A massive solar superstorm isn't a distant what if. It's a real scenario that space agencies are actively bracing for. The European Space Agency recently conducted its most comprehensive stress test to date, simulating the aftermath of a Carrington-scale solar storm striking Earth in the modern era. The results were a stark reminder of how exposed our satellites, electrical infrastructure, and communication systems truly are. In this video, we'll unpack what ESA learned, why storms of this magnitude matter, and what steps are being taken to prepare for the next major event. Let's dive in. In October 2025, ESA staged a full-scale emergency drill at its Mission Control Center in Darmstadt, Germany. The scenario: a solar superstorm matching the intensity of the 1859 Carrington Event. The simulation was carried out in 3 phases, mirroring how real extreme space weather events unfold. Phase 1: the solar flare. An enormous X-45 class flare erupted from the sun. Within 8 minutes, high-energy radiation slammed into Earth, instantly disrupting radio networks, GPS timing signals, aviation communications, and radar systems. Navigation accuracy dropped sharply, and timing-dependent technologies were among the earliest casualties. Phase 2: the particle storm. Roughly 10 to 20 minutes after the flare, a surge of energetic particles hit Earth's magnetic field. In ESA's simulated environment, satellites such as Sentinel-1D suffered critical electronic malfunctions, even with their usual radiation protection. Operators had almost no time to react before systems began failing. And then the Phase 3, the CME. Between 10 and 18 hours later, a massive coronal mass ejection collided with Earth's magnetosphere. The resulting geomagnetic upheaval induced grid-level electrical surges, expanded the upper atmosphere, and boosted orbital drag by a factor of 4. Many satellites in low Earth orbit lost stability, some beyond possible recovery. ESA officials summed it up bluntly: there are no perfect solutions during an event like this. The mission wasn't about prevention, it was about measuring impact and response speed. A superstorm unfolds in stages. First, a blast of X-rays and extreme ultraviolet light, reaching Earth within minutes. Next comes the particle barrage, capable of damaging onboard electronics and disrupting satellite operations. Hours later, the CME arrives, a gigantic bubble of plasma and magnetic fields that crushes Earth's magnetosphere and drives intense geomagnetic storms. These storms can degrade communications, destabilize orbiting spacecraft, and overload terrestrial power systems. The infamous Carrington Event generated vivid auroras near the equator and caused global telegraph failures. Today, with our deeply interconnected digital infrastructure, the stakes are far higher. A comparable storm could jeopardize satellites, communications links, global positioning systems, and electrical grids. In 2012, a powerful CME narrowly missed Earth. Studies suggest it would have caused trillions of dollars in damage had it struck. These events are uncommon, but far from theoretical. Statistically, a Carrington-level storm occurs every century or two. Preparing isn't optional, it's necessary. Unlike purely theoretical models, ESA's exercise focused on real-world operations, how quickly teams could respond, which systems would collapse first, and where emergency resources would be essential. Solar storms can't be prevented, but early detection can buy critical time. Even a few hours of warning can allow operators to shut down or shield vulnerable assets, a small window that makes a huge difference. A severe CME forces Earth's upper atmosphere to swell, increasing drag on satellites in low orbit and knocking many off their intended paths. Communications and navigation constellations could deteriorate within hours. Radiation blasts could also damage spacecraft in higher orbits, including those parked in geostationary positions. ESA's analysis makes it clear No orbit is completely safe during an extreme solar event. On the ground, geomagnetically induced currents can overload power transformers, damage transmission lines, and disrupt precise timing services. Systems that depend on GPS, aviation, shipping, telecommunications, and financial networks could experience widespread outages and dangerous navigation errors. The ripple effects would reveal just how reliant modern society is on steady, predictable space weather. ESA's preparedness strategy combines procedural planning with technological upgrades. Missions like Sentinel-1D will follow automated safety steps during severe events. The D3S, Distributed Space Weather Sensor System Network, will provide rapid monitoring of solar activity, and Vigil, launching in 2031, will watch the Sun from the L5 Lagrange point, delivering early warnings of Earth-directed CMEs. Space weather ignores national borders, which is why ESA's efforts are linked to an international system of data sharing, coordinated protocols, and unified emergency response plans. Just like pandemic preparedness, the first hours after detection matter most. Coordinated global alerts can reduce damage, protect key infrastructure, and prevent cascading failures. We're currently near solar maximum, the most active phase of the Sun's 11-year cycle. This increases the likelihood of major flares and CMEs. ESA's simulation isn't a one-time exercise. It's part of a larger push to get ready before a real event occurs. A Carrington-class storm isn't science fiction. It's inevitable. ESA's work makes it clear that the danger is real, but preparedness can turn a potential catastrophe into a manageable crisis. Early warning systems and coordinated responses could be the difference between widespread failure and a controlled impact. As we move deeper into an age defined by satellites, global networks, and digital infrastructure, understanding space weather is no longer optional, it's essential. The Sun will continue to surprise us, but how we prepare determines how well we endure its next major outburst. If you want to stay informed about solar activity, space weather science, and the technologies protecting our modern world, make sure to like, subscribe, and join us for future deep dives. Until next time, stay aware and stay prepared.